Welcome to Correlations and Other Statistical Inferences, presented to you by me, your host, Todd Levenenko, owner and consultant for TWL ICT Solutions. We will be looking at linear relationship, and this is part 2 of the series. We will be using a little script that I wrote in Python that I call linear number generator. Here we import random, a function in a library that will be used to generate a bit of randomness in the data. We will be writing to a file called linear.csv, and we will be running with a linear equation of 40.5 plus 3 times x. Once we finish writing the file, we will naturally close it. Okay, let's get started. As before, we're in RStudio, R version 3.4.4, someone to lean on. As before, we need to load some libraries. And the libraries I'm going to load as before in randomness part 1. Here we're going to be talking about linear relationships, and as shown in the previous slide of the Python application that I wrote, we have to read the PyCharm datagen linear.csv file, and we have allocated it to the variable linear. As I failed to mention last time, the parse with column specifications, if you do not define what column specifications you are looking at, the default is double. That is, the value of each coordinate is double. You could have it changed to integer or to Boolean or whatever else, character, what have you. Now, as before, I'm going to view this data, and when we view it, and we'll view linear, you'll see that I have an x coordinate and a y coordinate from minus 50 to plus 50 for the x, and the y is a value that has been determined by the equation, plus I threw some randomness in it to help define. And you'll see in part 3 why I throw randomness into an R equation. As before, I'm going to assign x to be linear $x and y to be linear $y. This allows me to do some programming where I don't need to define linear $x and linear $y into a plot. I just say plot x and y, and when I do that, you will see that I have pretty close a straight line. If I zoom into this, you will see that the data is almost linear. For the most part it is. I threw that randomness in to allow us to see what R is going to represent in this equation. As before, I'm going to now do a summary, and you will see that the summary shows that I have a x range and a y range. Minimum is minus 50, and for y it's minus 107, and for a maximum it's 49 for x and 190 for y. The median and mean are pretty well identical at minus 0.5 for x and 46 for y and 44 mean for y. Of course, that's because it's not truly a linear equation. I have a bit of randomness in it. The correlation test will tell me that I'm pretty darn close to a linear equation. As you could see my core test shows that it's 0.9993577. And as mentioned in part 1, when you have 1, that's ideally a perfect linear equation, and 0 is a total random equation. As before, the data frame x comma y I'm going to create, and I'm going to do a linear model of y and of x, which is y, to the value of x. I give that a model, and then I do a summary of that model, and you will see that the p-value for that value is pretty well 0, which indicates that the data is a well fit. Our r squared value is 0.9987, which is basically a 1. And what's different here is you could see that the significant codes in the intercept and the x relationship. The intercept is 45, so we would see that the value is 3x plus 45.5. The p value here is less than 0, and the probability of t, the absolute value of t being greater, is 2 times 10 to the minus 16, with a significant error code here of 0. If there was only 2 dots here, it would be 0.001, 1 dot 0.1, a period 0.05, and a 1 is 0.1. So as you can see here, unlike in part 1 of the full randomness, the significant code is very significant. It's basically saying it's 100%. With that said, we could now look at the plot model. I'm going to plot the model, and we will see some interesting relationships here. First of all, residual versus fitted. It's a line that suggests that the data is well fitted. As you could see by the curvature here, it's pretty well fitted. You'll see that there's a little bit of a curve here, but it's relatively insignificant. If we look at the normal Q, a lot more interesting data. You could see that it's showing that standardized residuals against the theoretical quantities of the function of x, relationship to x, is well fitted. Scale location of the standardized residuals to the fitted values of the linear model, again, is well fitted. And standardized residuals against the leveraged linear model is again well fitted. We could see that they would suggest that there are some outliers, 2 and 3 and 12. That is, the 12th piece of data is considered outliers. And that's basically it from a linear relationship. Thank you for watching. I hope this was informative.